just say to the listeners, don't give up. It might seem really complex, but once these concepts click, you'll know it.
I mean, if they've made it to the end of this hour and a half episode, hopefully, I mean, we probably should have said that at the beginning. Maybe that's what you can do. Insert insert that clip at the beginning, Bob. Welcome to another episode of ArrayCast. I'm your host, Connor, and today we have two panelists, and one subject matter expert, and I'll have them go around and introduce themselves. We'll start with Adam, then go to Marshall, and then go to Bob.
I'm Adam Polzewski, full-time APL programmer at Dialog Limited.
I'm Marshall Lockbaum. Today I'm known for creating BQN. I started as a J programmer and worked at Dialog for a while before that. Been through a few languages.
And I'm Bob Terrio, and I'm a J enthusiast. I'm expecting to learn a tremendous amount because I did a little bit of homework last night, and I've realized there's a whole lot of things I don't know about the topic today, and I'm going to find out a lot, I'm sure. And Stephen Taylor, who's our regular panelist, is not here because he's celebrating the 92nd birthday of his mom, and his mom is Belle McDonald. So happy birthday, Belle McDonald.
Happy birthday. A little bit sad that she took priority over us. Don't really understand that, but it is what it is. I'll give him a pass this one time. And yes, as mentioned before, my name's Connor. I'm not an APLK, BQNJ, or any other array language developer, but I am a huge enthusiast of the language and the combinators. I code in C++ day to day. And I think we have, before we jump into our topic today, I think we have three announcements, one from each of the individuals. So we'll go to Adam first, then to Marshall, and then to Bob.
Right, so after over 55 years, APL finally has a logo. It took like about half a year for the APL community to establish a logo that people found acceptable. And now that it's available, it's time to go and show your APL pride. So we'll leave in the show notes links to a store where you can get merch of various sorts.
Do we actually have merch?
Of course we have.
Really?
Yes.
There is merch. Yeah.
Since when?
There's mugs.
Since last week.
Really?
Yeah.
Oh, I'll have to go get some merch. I thought we were just joking because the last time we mentioned merch, it was Aaron Shu's site because we didn't actually have merch. But it's not merch for us. It's just
It's APL.
APL merch. All right. Not a Raycast merch.
Not a Raycast.
But the second best thing, I guess. All right. Over to Marshall.
All right, so after 2 years now, BQN is getting something that a lot of people have asked for, which is a foreign function interface, which you can use to call native functions like you would write in C or maybe these days Zig or Rust or whatever. So we're still kind of polishing off bugs with this, but I expect by the time that this episode comes out, we'll have released our foreign function interface. So if you wanted to use BQN but we're stuck on interfacing with other languages, that's a big step.
Awesome. That sounds super cool. And Bob?
And we had a listener email us and mention that there was a change to KX's terms of service in terms of the use of the free commercial license. And so we reached out to KX to ask them, well, for one thing, we asked them if they'd like to be on a future episode, but also we asked them if they had any statement. And they provided this statement, and the statement I will read right now. In early May, KX implemented changes to our free non-commercial licensing. This was in direct response to a significant breach of our terms of service. We continue to support our valued developers with access to free 64-bit on-demand tooling, curriculum, and community platforms. Over the coming days, we will launch the new method to obtain a license, but for now, kindly ask that you reach out to trial@kx.com with any requests. And of course, we'll put that link into the show notes. And that was their response to the questions about their change in terms of service, and that's their announcement.
Awesome, yeah. So probably at minimum, when Steven's back on in a future episode, we'll discuss it a little bit. Maybe there'll be a whole episode if KX wants to bring someone on, or maybe they send Steven. Send sounds weird, seeing as he's here usually all the time, but yeah, stay tuned for updates in a future episode, as we'll probably be mentioning this at least again in the future. All right, so that means today we're going to be hopping into sort of a roundtable discussion. I will be playing the role of noob, for lack of a better word, someone, beginner, on what I think is one of the more complicated topics in the array language paradigm. And that is sort of the idea cloud of rank, leading access theory, and, adjacent topics. So I guess I'll start by saying that this is probably one of the things that I understand least well, especially when it comes to J. Although compared to APL and BQN, probably I know the least about J. But there's been many times where I've been trying to do something in J, and I think the idiomatic way is to use the rank operator, which is the double quote. And then I'll end up like failing to do it. And I guess we should just start by someone explaining what rank is, maybe what the rank operator is, how it exists in each of APL, BQN, and J. Are there differences? And then from there, maybe we can talk about leading access theory, the development of that, how that sort of exists in the different array languages, because I know that there are differences between the two. We'll, at the top of the show notes, we'll have a link to the APL Wiki article on leading access theory, which has a couple different sections. The one most interesting one that I came across is called the adoption in APL, that shows that like certain glyphs, they operate on different axes, and when this whole leading access theory started to develop, certain glyphs you could basically work compatible with this leading access theory, but others weren't, and et cetera, et cetera. And across the APLs, there's this nice little sort of green and red diagram. But enough said from me. Who wants to start by trying to explain what rank is, what the importance of it is, and how it ties into leading access theory?
Well, I'll start by saying for the rank operator, the shocking answer for the differences between J, APL, and BQN is that there are pretty much none. It's probably one of the very few things where this is the case. I'm not even sure I can think of any others. There may be the reverse function, but even then, APL has the two reverse functions, and only one of them is the same as BQN and J's. I think Adam's probably the best person to explain kind of how you use the rank operator most of the time.
Okay, I guess I can I can try. But I would say that it has to be clear what exactly axes mean and leading axes, and defining a function in terms of leading axes first. Otherwise, the rank operator really doesn't make any sense. So in, I don't know, what should we call them? Proper APLs. Then data is stored in multidimensional arrays. And that means that you could define them in we call it a Revel order, just the order that they appear in. But then they're arranged along 0 or more axes. There are slight differences in the array model between APL, J, and BQN, but for our purpose here, that doesn't really make a difference.
Well, an array of numbers is the same in any of them.
Yes, yeah.
That basic concept is going to still work.
Yes. And so the axes are ordered. You have a leading axis, and then you have the next axis until you run out of axes. So for example, for a table or matrix, the leading axis in all these languages is considered the one that runs along the rows. So then we talk about major cells, which are, it's kind of like elements, but it's kind of like sub-arrays where you drill into an array. So a matrix is conceptually made of vectors. It's a collection of vectors of equal lengths. And so that traversing over these vectors, where you look at the first vector, look at the second vector, which are then the rows in the matrix, that would be the leading axis. And then traversing over elements of each individual vector is, in this case, the trailing axis. There are only two of them, so first axis and second axis. And so the important thing is that the more of a kind of a global scope that a function have, meaning when you feed it an array as argument, it applies to the whole array, the more you can, in a sense, force the perspective of the function to look at subparts of the array. if the function only by itself naturally looks at smaller pieces of the array, there's nothing you can do to make it look at greater parts of the array. Even if you were to try, then it would still drill in and look at small parts. So this might sound very theoretical. Let's make it very practical. Let's say in all these languages, we have two matrices and we add them together with a plus. It's identical in all these languages. So matrix A, matrix B, and we do A plus B. Now, plus is defined as in terms of nitty-bitty detail. So it drills into these arrays until it hits atomic numbers, and then it adds up corresponding numbers in the two matrices. And there's nothing you can do to make plus have, so to say, a larger perspective. It will just look at individual numbers and add them up. A function that doesn't behave like this would be the match or equivalent function. It takes two arrays and then it looks whether or not they are entirely identical. So it never looks, well, it obviously has to look at the individual elements of the array, but it never considers them separate from each other. It only looks at them as part of the whole array. And here you could conceptually narrow down the scope of the match function so that instead of looking at the whole array, let's say we talk about matrices, we could tell it to look at individual rows. So if we have 3 rows in both matrices, then we can say compare row-wise. So that's a narrowing down of the perspective of the match function. And that is where the rank operator comes in. It's a way to force any particular function to never see arrays of higher rank than a certain limit that we give it. Or in other words, it's a way to make it conceptually loop over an array and process it piece by piece. So that is what the array, the rank operator is all about.
And there is one other thing with the rank operator, rank operator, but ranks that you should know. We're actually talking about 2 different ranks. One is the rank of the object we're working on, and the other is the rank that's inherent in the verb or the function that we're working with. And the idea of the rank operator is to match one to the other. So by changing the rank operator, you can match your verb or your function to the array that you're working on, so you can access parts of the array. If you didn't have a rank operator, you're going to be relying on the function's rank alone, and it's always going to work the same way on the array. And the size of the array or the number of dimensions of the array will determine then, if you didn't have a rank operator, you would only be working maybe with leading access, and you'd have to change the number of dimensions in order to work with a different access, or transpose the matrix, move it around so now your leading access is something else. The rank operator allows you to zoom in, as Adam said, into part of the array and say, I only want to look in the object, I only want to look at rows. I'm not concerned if there's 40 rows or 50 rows or 1 row. I'm only looking at rows, and I'm comparing them to whatever I've got on the other side of my function, if I've got a dyadic function. So that's what the rank operator does. I think Henry Rich says something about it being like an impedance match in electronics. If you don't match them up, you're never going to be sure about what you get, and a lot of times it's just not going to work. So that's where a lot of times you see length error or something like that in J that indicates that you actually haven't matched things up. You're trying to match 2 of one thing to 3 of another. The 2 of one thing might be rows and the 3 of others might be blocks. And you've just matched them wrong. If you match them row to row, you might find they all match up again. And that's what the rank operator allows you to do.
Yeah. So there was some, I think, J-specific phrasing there. One thing that J has that APL and BQN don't is the idea that a function has this built-in rank that it uses. And so in J, you'll have the raise function that combines 2 lists, or that combines a list of lists together into one big list. That's given by J a rank of 1. So if you apply it to an array, or no, that one
maybe a better example I think would be, it seems kind of extreme, but there's the do verb in J. It's very easy to understand. So the do verb is just an eval. It just evaluates a vector, a line of code as J. But the important thing is, of course, that since J is a one-dimensional programming language, then it will you never want to consider anything that has higher dimensionality than one. And in J, then, since it's defined as having rank one, if you give it a higher rank array, it will just go in and split it up into little pieces that are all rank one. So let's say if you have a three-dimensional array, then it will consider like a two-dimensional array of one-dimensional arrays, and then evaluate all of those as lines of J and collect the result together. Whereas, say in APL, it would just error saying you cannot apply this function to a multi-dimensional array. It just isn't defined like that. You have to do it manually.
Yeah, well, so I mean, there's APL and BQN could define their evaluation functions to do something like this. But the difference in J is that each function has this concept of what is its rank, which other parts of the language can see. There's the normal atop operator written with an at looks at the function rank of its right operand, and the one with a colon doesn't. So in J, you have this built-in function rank, and you might even have a function that does the same thing. Like if you wrote execute rank 2, then J would say, well, this is a function with a rank of 2, even though logically it does still have rank 1. The J engine no longer knows about that. So, well, that's actually not a difference in the rank operator at all, but that's a difference in how rank is treated. So J builds rank deeper into the language itself.
But we can give an example of a very simple example of using then rank in say J, where it's even though the rank operator, the do or evaluate verb is defined as having rank 1, so it will only ever apply to lines of code. You could use the rank operator to apply it to rank 0, that's individual elements. So let's say you had a character array of digits and you evaluated each, then you would evaluate each digit in this character array and they would become all numeric instead. So this is an example of narrowing down the scope. So the evaluate function will never see entire lines. It will only ever see one character at a time and then evaluate those.
Yeah, so it would still ask what are the rank 1 cells? Like once the rank 0 is applied and it maps down to a character, it asks what are the rank 1 cells of my argument. But then the argument is a single character and it can't go down any further. So there's still that layer there. It's just not doing anything.
All right, so this has been great. I've learned a couple things already, which I'll summarize. So one, and this was, I was going to ask the question that Marshall immediately answered before asking it, so thank you, Marshall, is that this is something that's always confused me about J, and I didn't realize it was different between APL and BQN, although maybe implicitly I knew, is that J is different in this regard. It has this function rank, and it's actually exactly what you talked about, the at and at colon, which I think you said are the atop. I can never remember the combinators in J.
Well, I think pretty much everybody agrees that those two are the wrong way around. Mostly the colons are on the wrong one that should be the full rank version, and the ones without the colon should be the close version is what it's called historically.
Interesting. So there's even some agreement that there's a mix-up. But even what you just said right there is that the fact that there are two different versions of these, and like I absolutely love combinators. I study them like in my sleep because I love them so much. And like in between BQN and APL, like I understand them like very, very well. The only time I ever get mixed up is the fact that BQN removed the double dot, and so now those are two like opposites of each other. Because the B1 combinator at top doesn't have the double dots, and anyway, so that doesn't really matter. Listener, you can ignore that. But the point being is that J has this difference, and it has always confused me, especially that one diagram, which we can find the link for, that shows a visualization of the sort of composition patterns of the different ones, and there's a bunch of like arrows. Like I've never understood that diagram, even though I have to admit I haven't tried that hard. But the point here being is that J is slightly different, and so maybe we can come back to this in a bit. But I think we should circle back to the start of this discussion and just talking about rank and sort of the wording that Adam used is narrowing down the scope. as I will sort of restate a couple different examples and then ask a question after this, just because probably all our advanced array languagers that are listening, they've understood everything so far. Maybe they learned a couple things like me, but there might be a couple beginners that are just totally like, what are folks talking about here? Like narrowing down the scope. We've got different functions that operate differently. So the example that Adam used was the plus, which I think is kind of, that's a scalar operation, and I put like scalar operations in a different category, which I also think that'll be sort of my following up question is, what are the different categories of functions or glyphs in these languages?
Well, I have a quick answer to give to that. So the only categories that matter for rank are really the scalars and everything else. But what actually, the direction I think Iverson was going when he introduced this rank idea was that, scalars, of course, have rank 0. They only work on, an atom or a unit or whatever at a time. So Iverson wanted to, instead of having just 2 categories, have instead the rank of a function as a more general attribute that allows you to say what a function is. So, now you can say that there are infinity categories. There's rank 0, there's rank 1, there's rank 2, and for dyads, there's rank 0, 0, and 0, 1, and so on. You can have one rank for either argument. So there are only 2 categories, but rank kind of generalizes that idea so that you can say something about the functions that aren't scalar functions.
Okay, so I'll have a follow-up question. Maybe I'll just ask the follow-up question. So, and just to be clear, for once again, the beginner that's listening, when we refer to scalar operations, we're referring to like the classically, like all the mathematical operations, plus, minus, multiplies, divides. There's a bunch more, but like there's this category of operations that, at least from what I understand in APL, if you can add the 2 atoms, 1 plus 2, you can add a scalar, a 1, to any rank array, whether that's a matrix, a list, n rank matrix, and then it'll just add that scalar to every individual atom. And then you can also, it works polymorphically if you have 2 arrays with the same rank and shape, and then we'll just add them together. But I think after that, APL stops working because you can't add a row, like you can't add a rank 1 array to a rank 2 array. You can't add, a vector to a matrix. Although, hypothetically speaking, you could, right? You could just, on a row-wise basis, add everything together. And I think that's where rank comes in, if you can use rank on scalar operations. But
yeah, and this is going to tie into actually the one small difference that APL has versus J and BQN, which APL could still extend to get up to the functionality that J and BQN have. But right now it doesn't do this leading access agreement. Or actually, does the rank operator does it? Doesn't it?
No.
No, it doesn't. It just has scalar agreement for the rank operator. So yes, in J and BQN you can add a list to a matrix or anything like that, and that's the one difference there is still in the rank operator.
And can you do that in APL? I don't think. No, or is there a way to do that? Yeah. So like,
well, you have to use the rank operator.
So if you go 1, 2, 3 plus rank insert 1 or whatever rank you need to, and then to a matrix.
-1 would be the rank that you want to do the same thing.
It doesn't actually matter in this case, but yeah.
Okay, so -1.
No, rank 1 would be okay, it depends on
what you want to do. Yeah.
So
if you want to add it on a row-wise basis.
Are we ready to go to leading access ideas yet?
Yeah, I think I was going to say, I think leading access is, you sort of touched on it when you talked about scalars being added to matrices, because at least in J, scalars have an empty shape. And that means they'll match anything for their preface, which allows them to be added to like a matrix, a 2x2 matrix, because they match everything.
Yeah, but the same would be true if you had a trailing access agreement. So it's when you're adding a list to a matrix that you first get, in arithmetic at least, these leading access ideas showing up.
Yes, but yeah, you're right. It shows up as something that you can see But the reason it works for scalars is because you don't see it, but it matches everything. And you're right. If you had, say, a list that has a leading dimension of 3, and so it's a list. It's just a single, 3 numbers, and you're adding it to a 2 by 3 matrix. In that case, if you just try and add them, and you try and add it, you're adding 1, you're adding 3 to 2, right? But if you make it rank 1 and you look at lists on both sides, now they match up. And the reason they match up, yeah, go ahead, Marshall.
Yeah, and so this is where array programming will trip a lot of people up, because definitely NumPy, and I think Julia as well, will match the trailing axis instead. They'll say, if you want to match this list to this matrix of lists, well, yeah, I'm going to match the rows up. And so APL goes in the other direction with respect to the axes, but there's a good reason for that, so I'm sure we'll get to it.
So the question is, do we want to start talking about leading axis theory? I'd say let's come back to that, because I still think that I have a question for Marshall and everyone, but the question came from something Marshall said, which was these categories of functions, and you sort of group them into scalars and then everything else. And so we talked about scalars and how in APL for the plus operation and other scalar operations, that's going to behave differently than BQN and J. And in order to get that behavior where you're trying to add a single vector to a matrix, you're going to have to use the rank operator, which I just opened up a RIDE editor and sure enough got it to work, where I added 1, 2, 3 to a matrix of 1, 2, 3s and had to add some parentheses so that the ones didn't collide with the shape of the matrix, which is irritating, but it is what it is. And
it's not in BQN.
Yes, that's right, because of stranding. But so everything else, is that really the case? Because on the leading axis theory page of the APL wiki, and this is actually, I stumbled across this discovery, or whatever you want to call it, in the last couple months, is that I didn't really ever observe that there seems to be more categories in this everything else, because a lot of what I think of as like bread and butter operations in APL, because they're the ones that I first stumbled across, are reduce, scan, and reverse and rotate. Because I love rotate. It's got a lot of sort of jokes and memes in the C++ community of that's a rotate. And so when I discovered there was a rotate in APL, I fell in love with it. And all 4 of those operations, reduce, scan, reverse, and rotate, are all I referred to them in my head as axis last operations, but it sounds like we just referred to it as trailing axis operations. I'm not sure if there's an actual word, but on the leading axis theory page, it has this table, and it refers to, like, in one of the rows of this table, it says uses first axis form only, and then proceeds to list off reverse, rotate, replicate, reduce, expand, scan, and concatenate. So all 4 of them showed up in that single row of what I thought were like I think bread and butter is like the wrong terms, but like some of the first verbs that I really learned and like associated with the language. And then I discovered later on that not all verbs or functions work that way on the sort of last axis, and we'll correct my terminology if it's the wrong terminology in a sec, compared to like operations like match or unique that operate sort of, I didn't have the words for it, but it's on the major cells versus the last axis. So I guess my question, 1 is, am I using the wrong terminology? 2, is there more of like buckets of functions within the non-scalar operations that you sort of said everything else? Are there different buckets of functions that some work on what I call the last axis, some work on the first axis? Although that's the confusing part, is that this table that I consider the last axis functions refer to them as use first axis form only. So there's a lot of confusion here on that. Like, I feel like there's this kind of taxonomy, like implicit taxonomy, but my guess is that array programmers, it's not implicit for them, and they actually they know the categories of stuff. Anyways, yeah, I'll stop talking.
Well, okay, so what's happening here is that each of these functions is actually, well, and operators, is actually two operators. So there's one that would have been considered at the beginning of APL, the normal version, which are the ones that you saw that act on the last axis. And then there's also a first axis form that's written with a horizontal bar somewhere in it. So for slash, this is the slash bar, either slash. For rotate, this is the ugly one that's sideways. And there are a few other. I think mostly it's just with a bar added to it. And so those are the first axis forms of those functions. So I don't know if there's really any name for all of these. I would call them probably paired functions that have two axis forms. Just explain it.
So to be clear, just to clarify what Marshall's just pointed out, is that the reduce and scan that are listed in this table that I'm referring to are actually the reduce first and scan first with those horizontal slashes in them, which I have completely missed, in that those versions aren't actually the last axis versions. They are the first axis.
Yeah, first axis. And first are leading, last and trailing. Those are just equivalent.
First and leading and last and trailing. So technically my terminology was correct.
It's fine. You just didn't know about or missed the first axis versions of those functions.
So why actually are reverse and rotate? Aren't those last axis? Or are they actually
the two of them in APL, right? There's the one in APL, the symbols for them are a circle with either a vertical or a horizontal bar. And that bar indicates the, so to say, the mirror surface of when you're dealing with a matrix, at least. So the vertical bar, if you use them inadequately, so circle, vertical bar, circle style, it mirrors right, left, right? And the one the circle with a horizontal bar, it mirrors top down. So I call it flip sometimes. Flips
so yeah, I've misread this one row in this table twice. I've missed the horizontal lines, and also it says reverse comma rotate, and then in parentheses the horizontal, as Marshall said, ugly version of the vertical one, and that applies to both reverse and rotate. For some reason, my brain read that reverse, and then there's a missing vertical line with a circle, which I don't know why my brain was putting that there. And then when I saw rotate, I was like, oh yeah, that's the rotate glyph. That's supposedly different than the vertical line one. So my brain just completely misread this. All of these are the first axis versions of reverse, rotate, reduce, and scan. Interesting. Okay, so a part of my confusion is that I can't read.
I think it's true for all of the first axis ones. Whenever there's a pair, first and last axis, then in APL, all the first axis ones will have a horizontal bar as part of their symbol. So you've got comma bar, comma with a and a minus on top of each other, kind of, and you have the circle bar, and you've got slash bar.
And is this why more typically when I see array language people writing in APL, they prefer the reduce and scan first glyphs to just the regular slashes? Is this the reason? Is because...
Yes, definitely.
Interesting.
Well, so yeah, we haven't gotten into the reason why you would prefer this in the leading axis model.
We can do that now if you want. We can do that now.
We kind of have to talk about that.
Yeah.
So the idea is, we've said what the rank operator does, which is basically that it allows you to, it lets you to specify that you're working on the trailing axes. And another way to look at that is to say that you're mapping over the leading axes. So the thing that these leading axis functions do, like if you have your plus slash bar function, which is going to do a sum, you might say it sums the columns of a table, but really what it's doing is summing the rows together. So it adds one row to the next row to the next row. What rank allows you to do with that is if you use this plus slash bar and you call that with rank 1, then it's going to sum the cells of the rows of the argument, which is actually summing each row. So this plus slash bar allows you to sum in either direction of a matrix, and more generally you can sum along any direction in a higher rank array. And the simple plus slash, it's always going to sum the rows. And if you tell it the rank, it doesn't matter. Like if you say, all right, I got a rank 3 array, I want to do plus slash on rank 2 here. Well, then it's going to say, all right, I'll do whatever I'm going to do on each block, on each 2 cell of the array. And the thing that it does is to sum each 1 cell. So it's still the exact same thing, summing each 1 cell. So the idea, and this is the core of the leading axis model, is that having rank map over the leading axes and then defining your functions to work on the leading axes gives you this whole flexibility to work on any axis if you combine them together.
That is such a good... Oh, sorry. I got a little excited there. That... I never... Yeah, I just totally... I hope a couple listeners just had the... I wouldn't say epiphany, but understanding from what you just said there. Because that is, I think, extremely non-obvious based on the default behaviors of reduce. We'll stick with reduce because I think that's the easiest to explain on a podcast, is that if you compare reduce versus reduce bar or reduce first, and you apply that, a plus reduce, summing to a matrix, when you use reduce, it sums up row-wise. And when you do reduce first, it sums up column-wise. And so that's how I just think about those two. It's like, oh, one does rows and one does columns. But really, it's not doing that. Like functionally, that's what's happening. But it's what you said. You're summing the rows of a matrix or summing the elements of a row, which then end up having the same behavior as what I just described. But when you just stumble on the language and you start playing around as, oh, what does this do? What does that do? It's completely non-obvious that that's the actual behavior if you're just messing around with sort of rank 1 vectors and rank 2 matrices. Bob?
For reduce in J, what you're doing is whatever your operation is, say it's addition, you're adding items. And items are the -1 rank of whatever you're adding. So if you're in a matrix, a table, your items are now rows. So you're adding rows because you're adding items. When you have a row and all the items are atoms, now your items are now atoms. And so reduce is actually summing, in this case, items. And items can change depending on the shape of your array. If you have a 6-dimension array, items are going to be your 5-dimension, whatever you'd call them, blocks, hyperblocks. Those will be added together because you're adding items. And you've got a 6-dimension array, so each of your items is going to be 5 dimensions.
That's what I was calling major cells before, which is a bit of a technical term. The idea is...
Yeah, that's the APL.
Yeah, the idea is that you look on your array as a collection of arrays of a lesser rank with one less dimension. So there's you can look at it as an outer dimension and then a bunch of inner dimensions.
But
and so there...
Yeah, this is really a non-obvious thing. Epiphany is absolutely the correct word for it. And specifically, this epiphany happened to Arthur Whitney on a train to the APL 82 conference in 1982. But to explain how non-obvious this is something that I found out kind of recently, and I checked my memory on it today. Iverson and Bob Bernecki basically described, they actually did define the concept of function rank, but not the rank operator, in a 1980 paper called Operators, Functions, and Enclosed Arrays. And in that paper, they described an axis operator that says specifically which axes you want to work on. And so you have to list out all the axes, which is kind of weird. And also, not only that, the argument axes you can select any ones. But then once your function operates, the result axes all go to the end of the function. So on the outgoing end, it actually works just like the rank operator. But in the ingoing end, it's much more complicated and weird. But they actually did describe function rank, and they said the rank of a function is just the number of axes it works on. So like reverse last, they would have said that's a rank 1 function. And that concept was already there. But it took 2 more years and Arthur Whitney, which is, throwing quite a lot of processing power at it, to develop the idea that actually all you need to do to have, pretty much as much flexibility as you want, is to specify how many ranks the function has, and we'll just say these are all the trailing ranks that it operates on, trailing axes.
Interesting. That is...
I think we should include that this was a reaction to a problem in the design of APL. So we have to go way back to Iverson notation. So Iverson's notation, which is just like a generalization and application of traditional mathematical notation, and it looked very much like traditional mathematical notation, and it used a 2D paper to write his formulas on. And he only ever dealt, I think at least, with arrays up to rank 2, so up to matrices. And Iverson loved matrices. I have this from Roger Huey that Iverson loved matrices. And so when you're applying things, then there were only these 2 axes that you could ever work on. Right? So either you could apply the first axis or you can apply left axis, and that was it. And then you had I think you used like slash and double slash or something like that to choose the axis. Then when they linearized Iverson's notation into what became the APL programming language, meaning everything had to be discrete characters that could fit in a typewriter, then they solved this problem by adding what's at least later has become as the bracket axis, possibly bracket axis operator, but it's a little bit iffy to call it an operator. It's more like bracket axis notation. And that's the idea that after a APL glyph, you can write bracket axis. So you write open square bracket and then a number normally, and then close square bracket. And that tells that glyph on its left what axis to operate on. But it's very ad hoc to every built-in. So it might look like it does the same thing
right
on all of them. But in reality, if you try to formulate what the rule is, you can't, because each one of is entirely separately defined, and you cannot generalize this. And so this was, I think, quite early on recognized as a little bit of a wart, and also something, if you want to define your own functions, you couldn't use bracket axis because the system wouldn't know what it meant. GNU APL actually has generalized it so that you can in the header of a function, you can specify bracket axis, and then this function can choose what to do with that, and then they kind of abuse it for just as an extra argument.
They generalized the notation. Yeah. They didn't generalize the definition.
No, because you can't, right? So that's why they felt the need to add it as an accessible syntax.
Yeah, well, so that's why Iverson was developing an axis operator. His idea was I will take this axis concept and generalize it, and that turns out to be a pretty bad idea. Yes, it's possible, it's very awkward to use, and you've got this problem that not only do you want to know where the argument axes come from, you also really want to know where the result axes go to. So if you wanted to specify all that, I mean, that's a whole lot of numbers that you're throwing at it to do one operation.
Can you give because I don't think I fully grokked the axis operator. Is there like a simple example on like a matrix? Like it sounds like...
Well, so we'll talk about scan. So we'll say you're starting... Actually, I guess it's going to make more sense if we say you're starting with a scan operator that works on rows. You just have the non-barred slash. So then what you would do is use the axis operator and say, I want to run on axis 0, I think, whatever the first one is. And then what it would do would actually be to split up the argument into the vectors that go along that axis. It would split it up into its actual columns in that case and do a scan on each column. And then here's where things get really weird, is that the result of scanning one column, a column's a list, so the result is a list. And then it would put those results together into an array. But then you'd have the result of scanning on a column would turn into a row, because it doesn't know which axis they should make up in the result. So that's kind of the model they had going. That was the state of the art in 1980.
Wait, so let's make that example a bit more concrete. So you're doing a plus scan, and you specify axis 0, and let's say we have the matrix 1, 2, 3, 1, 2, 3, 1, 2, 3 in a 3x3 form. So it's 3 rows of 1, 2, 3.
Yeah, yeah.
What's the result of that?
It would break off the column 1, 1, 1.
Yeah.
Plus scan that, you get 1, 2, 3.
Yeah.
That's the first row of the result. Column 2, 2, 2, plus scan, you get 2, 4, 6. That's the second row.
I see.
So it's actually the transpose of the first
Right,
axis plus
right.
scan as we
Gotcha.
have in APL.
And you're saying the issue there is that potentially if you're doing a plus scan column-wise using this axis operator, you want it in the same form that you might see it using the scan first in APL where it wouldn't have the transpose result. Or maybe you do want it the way that it's doing it, but you're at the...
Well, almost always you want it the same.
Right.
You want what APL does now.
Right.
So, I mean, the problem is you have an arbitrary function. It takes some dimension of array in, like for matrix division, say it's 2 dimensions in and 2 dimensions out. And that's, of course, twice as bad because now you have 2 axes that you have to figure out where they go. And so Iverson wanted to be able to say, I'll take, even for a matrix product, this is actually an example they gave, a matrix product with rank like, actually, yeah, the one that was in the paper was axis operator 0, 1, semicolon 1, 0. So it's going to take the first 2 axes of the left argument and then the first 2 axes of the right argument, but reverse those axes, so it does a transpose. And then you do the matrix product, and then I guess those axes go to the end of the result. So that's just really complicated. And I mean, if you try to implement that, you can't implement that efficiently. There's no way. And so another nice thing about the rank operator is that because it always splits its arguments into cells, which come together in memory, it's very easy to pick a cell out of an array. And that means that if you write a function with the rank operator, it's going to have at least like a minimally efficient implementation.
Yeah, that is very that's very interesting. So I'm also starting to realize too that I think my mental model of going into this was not entirely wrong, but just I had this view of the taxonomy of functions that I said existed. Really, what it is, and you can correct me if I'm wrong, Marshall, is that in BQN, really it is just scalars and then everything else which works with the rank operator. I'm sure there's some functions that don't work with the rank operator, but all the ones that do sort of behave in the same way, which is why there's really only 2 categories. Whereas in APL, if you skip back to, I guess, depending on how far you skip back, the rank operator wasn't introduced into Dialog APL, or I'm not sure if it was introduced.
In Dialog, it was 2013 or so.
Version 14.
Okay.
So actually pretty recent.
And so it's that APLs weren't designed initially with this idea at all because it was a decade and a half before Arthur Whitney came up with it. And then since then, which is why they have this table, they've evolved the language such that they've added second versions of operators and functions so that they have basically like the leading axis theory version of it, which they call, they used to have reduce, now they have reduce first. They used to have scan, now they have scan first.
So that is actually the wrong way around.
So it's the wrong way around?
Yeah, these paired forms with the 2 axes, they recognized that it was useful. And so they add the 2 of them already. I mean, maybe you want to, and that goes back, even the paper A programming language had these pairs where, for example, it would have slash and you'd write actually 2 slashes for a reduction along the first axis of a matrix.
Interesting.
And in that way, you wouldn't even, because Iverson's, at that time, was really doing just matrix arithmetic pretty much. You never needed to say the axis, really. I mean, I think that he may have defined a bracket axis thing or some sort of axis specification. But he certainly didn't use them much in that paper, and he wouldn't have when he was teaching with APL. But those paired forms are there from the beginning, and the leading axis idea is that, well, you actually only need 1.
Well, you only really needed 1, even when they added the bracket axis, right? Because bracket axis will completely ignore whatever you give it. Again, it's ad hoc, so it doesn't matter if you say plus slash. So that's the reduction, some reduction, or plus slash bar, which is plus reduction on the first axis. It doesn't matter if you put bracket access after it. Then you'll just overwrite whatever its inherent thing is, and then along some other axis. And that was then a solution to the problem they had, that Iverson was using a single slash and double slash, and that wouldn't work in a generalized system with any number of axes. I mean, that would be unbearable.
Yeah, but it's in that case, the language isn't. Now it's not just providing you with two operators; it's providing you with a whole family of them. So, leading axis, you actually just define one thing, and then, as a matter of definition, can apply it to others. I mean, that's an aspect of composability in APL.
That doesn't mean they're not useful, by the way. Yes, they are sufficient.
Yeah, it just means that there are more of them. It's a more complicated language. You have to know more things about the language to be able to use it. What does access do on this function?
Yeah, but it does provide for some.
And I mean, of course, it was still revolutionary at the time, but I and a lot of other people think that this leading axis model is, well, objectively, it's a simpler language it leads to, and I think it's a better trade-off in terms of your language design.
So my next question, I guess, is, and hopefully the listener's still following along, and then maybe Bob, after Marshall answers this, you can comment if there's differences or in J, is that surprisingly in BQN, if you're coming from APL, you'll try and do plus slash, which is really plus fold, and it's a superscript operator. And if you try and do that on a matrix, it'll go, bah, bah, sorry, that doesn't work. And then you're like, what? This works in J, this works in APL. And then very quickly, because the documentation for BQN is phenomenal, you go to your little BQN to APL, dialog APL translator page, and then you look it up, and you have to add, I think what it's called, cells, which is another superscript operator. So all the operators in BQN are superscript. And so that means we have basically, and which cells is like I don't know how you want to describe it, sort of.
Cells is just rank -1. That's exactly what it is.
Or I was going to say, like, visually, it's like.
It's a brave symbol.
It's a little moon.
So
what was it called? A grave symbol?
Brave, BREVE.
BREVE.
Brave.
So it's kind of like a circumflex but rounded. Yeah.
Think it's a half
It's
circle.
a circle that
yeah.
opens upwards.
The bottom half of a circle, but
Yeah,
superscript.
we'll call it a cup. So in order to get it to work, you have to go plus slash, which is the fold, and then the cells. And so you have in terms of the superscript operators, and maybe you can add to this list, but so we have basically fold, scan, insert, which is basically like 2 slashes, and then the cells.
Yeah, an insert is actually the one that you want for talking about leading axis model. So the fold just works on lists. It's not actually a leading axis thing at all. Insert is the one that works like J, which is the two ticks. So I mean, they'll be pretty similar if you're applying to rows, but that's the one that does the leading axis stuff, is the insert.
And you were asking about J. As soon as Marshall said, cells are -1 rank. That's items in J, and that's how J handles it. It just refers to items.
Yeah, well, I mean rank operator -1 is the definition of the cells.
Okay.
In BQN, it's called a modifier,
But in J, they just assume that you're working with items.
Well, yeah, but if you want to sum the rows of an array, in J you have to write the number 1 or -1.
Right. Yes. Yeah.
And in BQN
right.
you just have one nice symbol for it. That's hard to describe, but it's easy to see.
Yeah, you've got a symbol that represents the -1 rank, as opposed to J, which you're actually putting the number in.
Yes.
Yeah.
Which is very nice, and is what you need to use like maybe 2/3 of the time even. So it's very convenient to have that.
Yeah, items or cells are very useful, no doubt about that. If you set up the other thing that is worth mentioning in this is all of this presupposes that when you got your information into an array format, you've put the information in the right order in terms of dimensions. Because if you mix up your dimensions, you can work completely against what you're trying to do with items or cells or leading access, and you're going to have to do a transpose to get it back to where you can actually use it efficiently.
Wow. All right. I just tested something while there was conversation for the last 30 seconds. So I just discovered. So, well, where do I start? So the double tick, which is called insert in BQN, is the same thing as reduce first, correct? In APL.
Not quite. It is the same as sharp APLs, reduce first, but which is where Iverson was working. But the APL2 family actually does something slightly different, which is it works element-wise. So actually, the dialogues reduce first is equivalent to J or B. Well, you can only really say it in BQN. It's equivalent to each insert. So it works on one element at a time. Well, the evaluation order, I think, is different, but it's the same basic idea.
It works at one element at a time, opposed to APL, which does what? Or dialogue APL?
It doesn't matter if you're using plus, because plus is already working element at the time, as I started off with. But if you use anything else, like let's say you use concatenation, then there's a huge difference, right? If you, let's say you have a matrix, 3x3 matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? Now, if the insertion here or reduction considers each row as a whole entity, and you then reduce, then you would have 1, 2, 3 concatenated with 4, 5, 6 concatenated with 7, 8, 9. Okay, so that gives you one long vector. Whether or not it's enclosed is not so important. If you do it element-wise, then it's kind of like concatenate each. So it would be 1, 2, 3 concatenate each with 4, 5, 6 concatenate each with 7, 8, 9. So essentially what you get is 1, 4, 7 are concatenated together, and 2, 5, 8 are concatenated together, and then 3, 6, 9. Those are the columns. So essentially in APL, if you do, so concatenation is comma. If you do comma slash bar, that's reduce first, on a matrix, then it will give you the columns as vectors. Whereas in J or BQN, if you do the equivalent, it will just merge together the rows into a single vector.
Okay.
Now you can achieve the APL result just by adding an each to J or.
Yeah, which is why I ended up. So I think of these as three different kinds of reductions. There's the pure list thing that only BQN has. Well, K also does that, but BQN among the multi-dimensional array languages has that. And then there's J's insert, which comes from sharp APL, and there's this APL2 family element-wise reduction. And I decided that the best combination was the first two of those because it's the easiest to get that element-wise version out of the insert.
So say those three versions again. There's a
pure list reduction. I mean, what you would see in Lisp or another functional programming language that doesn't really connect with array.
And that's your BQN fold that doesn't exist in Dialog APL or J, but does exist in K?
Yes, that's the only one K has, because K doesn't have, it represents multidimensional arrays as lists of lists, so it doesn't have any native multidimensional array type, and so the only thing that makes sense is to do a list reduction. Although you might actually say that's the same as J's insert. I mean, it sort of collapses these concepts together when you're representing arrays this way. Because you might say that, well, the elements of the list are actually the cells of the array, if you think of it as a multidimensional array. So K kind of has both, but in terms of what the implementation's doing, I would say that it's the list fold is what it does. So BQN is basically K's version that's split up into its two things. Well, what if you think of it as a list of lists versus what if you think of it as an array of cells?
Is your head hurting yet, Connor?
No. I mean, like, I feel bad for the. I don't. There's two categories of listeners. Like I said, there's the array programmer that thinks it's great that there's a podcast that talks about their favorite paradigm now, or one of their favorite paradigms. That's probably going, oh yeah, this is some bread and butter stuff. And then there's the beginner whose head's probably being like, you know what? I'm done with this paradigm because this is seems overly complicated. But that's just, I mean, admittedly, this is a difficult conversation because we've got, primarily we're focusing on J, dialogue APL, and BQN here, all of which have sort of overlap. Like there's a Venn diagram of these operators, and understanding that Venn diagram requires understanding this concept of rank and leading access theory. I thought that so just for the listener, BQN, once again, their fold is the superscript / and then the insert is a superscript //. I just realized, I looked up on JNUVOC, that insert is what they call the slash in J. So we've now got the double slash in BQN is called insert, and that follows basically J's insert, which I didn't even realize that J's insert and now BQN's double slash insert are both basically the leading access theory ones. And you said there was a slight difference between the APL, dialogue APL, reduce first, which is sort of the element by element, versus what's the terminology for not saying element by element, treating them just as items?
We don't know.
We don't know what the terminology is. But
it just does whatever it does.
Which is confusing because, the reason it's confusing is that for certain operations, the behavior is identical, which is, we had to switch the
for everything you could possibly do in APL 360, which was just arithmetic operations, reductions. They're exactly the same. There's no way to tell the difference, which is why when APL kind of split into this sharp family and the APL2 family, the flat versus nested models, they were able to extend this in two different ways. And either language could have chosen either direction, I think. I don't think that the element-wise thing would make much sense in the flat model in sharp APL. But
no, I think the leading access gives you a lot more power than the
well, they
element.
both work on the leading axis. It's just
oh yeah, I guess you're right. Yeah, okay, yeah.
It's just, do you connect elements across the leading axis, or do you just split it into cells?
And Connor, when you're talking about what a beginner's going to get from this, I think probably the best advice is probably pick one of these languages and work with rank on that. Right now we're talking about comparisons between the different languages, and that becomes quite difficult. Although if you know one of them, I'm learning a tremendous amount listening to how BQN and APL do it, because it clarifies a lot for me, because I understand J. If I was to suggest anything for somebody to understand, J's rank is probably, I'm trying to think of the chapter numbers, but there's 2 chapters of Henry Rich's book that really go into detail on rank of objects and then rank of verbs, which is what we call functions in J.
Yeah, I think verbs have rank is the name.
Verbs have rank, and we'll put links in, but they're excellent. And when you start out, it's going to take you several readings to get a sense of it. And if you really want your mind blown, you can stack the applications of the rank and do some very interesting things with that. So you can break your object into chunks and then take those chunks and break them again. And especially if you're working with something like catenate, which is infinite rank, you can do some amazing combinations with it. But that really is the power of rank, but that's not where you start out.
So what are I've come to the realization now that there are 2 different ways to sum the rows in a matrix with what is provided in BQN, and maybe it's the same case in J. The first way is plus slash, which is the fold, superscript fold, and then cells. How do you spell it with so that's numero uno, numero dos? Actually don't know what the next one is. Numero 2. I apologize to our Spanish speakers.
Oh, that's Spanish.
Is it? I don't know.
We're making up languages now.
It's dos.
Dos, thank you. I was surprised no one helped me out there. I just left me out to try. How do you spell it with the plus insert? And then I tried rank 1, but that does not do or I'm not spelling it correctly. Is there? I assume there's a way to do it.
That should work.
Oh no, yeah, it does. It does work. I just don't know math, right?
And you can use either one with cells too, with the cells modifier. The difference is that when you take when you do a sum with plus fold of a list, the result of that, and now this concept you can't even express in APL and J. The result is a number that is not an array. So it removes a layer of depth. When you do plus insert, what it's actually adding together are not the individual numbers, but 0 cells that contain the numbers. And so the result is an enclosed number. And so what you want is actually when you're doing a reduction on an array, like if you want to sum the rows, you want to use insert because the depth of the argument is the same as the depth of the result. And the reason why this is practically an issue is that if you have not a matrix of numbers, say, but a matrix of lists of numbers, say you've got a matrix of coordinate pairs, then when you do fold on one of these lists, it's going to add all the coordinate pairs, and the result is a coordinate pair. But then, if you take that with rank, then the result is going to say each of these coordinate pairs is a row of the result. So it's going to merge those all together into one n by 2 matrix, which is probably not what you want. Especially given that like this matrix could actually, maybe it would have lists of length 2 on the first row and length 3 on the second row, and so on. So you do want plus insert cells, because then the result of each reduction is going to be an enclosed coordinate pair, and the final result when it merges those together is just going to be a list of the pairs.
Mind blown.
And is that because it's a based system, Marshall? Is that what that comes from? Yeah.
Yeah, that's the reason. Well, you would have, like if you introduce this list reduction function to APL, you would have the same problem, but the difference that the based system makes is that there is a difference between an enclosed number and a not enclosed number. So you can actually see the difference even for lists of numbers. For APL, I would say that for lists of numbers, the problem is kind of like forcibly removed by saying that a number is the same as an enclosed number. But you still have the problem with a list of pairs of numbers or something like that.
And for J, we get around that by boxing because we're on flat.
Sort of. Same thing. I mean, if you had a function that took a list of boxes and summed the elements together, you would end up with that same problem if it didn't return a boxed value. And you just don't have... Yeah, where you get around the problem for a plain list of numbers is that you can't have a list of numbers has nothing like inside it in J. I mean, underneath you can say there are numbers, but if you try to take an element of the list, you still get a rank 0 array. You don't get like a plain number. There's no such concept. So it'll implicitly force it up to rank or to depth 0 because that's the lowest depth it has,
Mm-hmm.
which would correspond to depth 1 in BQN.
I'm thinking now about how I feel about all of this, because
Me too.
a part of me, I think the reason that I fell so quickly in love with APL was, just going to tryapl.org or .com or whatever it is. It's .org, right, Adam?
Yeah.
And then I just went, / iota. I think I did iota first because we have that in C++. And I was like, oh, took me one character, whatever, plus a number, where it stood : iota paren. And then you have to, before even that, you have to initialize a container, usually a vector, and then you gotta, it's just a mess. Then you gotta define the iterators, and now we have views. But the point is, took one character versus like 20 in C++, plus a whole hell of a lot of knowledge about where, things live in which headers and et cetera, et cetera. And then in order to add that list, I just went / and I was like, holy, that was easy again. And, and so the reason I'm saying I'm sitting here trying to wonder how I feel about this is that experience it's extremely, I think, easy for a newcomer to just like. I think there is actually something special about coming from C++ if you are not like if you are a curious person that is open to different paradigms and aren't going to be like, well, where's the performance graph on this? Is this faster or slower? If you're interested, coming from C++ really sets you up to sort of be wowed because of how succinct everything is, and there's a lot of stuff that maps from our algorithm header. But with this stuff, so like technically in a leading axis theory pure array language, maybe BQN, you might refer to it like that. But like if you were to remove the fold and just have the insert, and you wanted to sum the rows of a matrix, which I think, from my experience, is a very common thing you want to do when you're solving little, fun trivia leak code problems. It's a very common thing that comes up. You now went from plus / and just putting the matrix there to plus insert rank 1, which like I can see the argument of it's the better model. It's what Aaron Shu would say about when I complained about the power set expression in order to generate all possible combinations of whatever length, and I went to APL cart. And it was like, I don't know, 16 characters or something. And I was like, oh, come on. Like 16, like this is way more complicated than I thought it should be. And Aaron had this response talking about, it's when you really learn the language, all the little tools and pieces that you need to build up that expression, like give you so much more power at the end of the day. But then there's always this argument, or there's this line of like, how much power do we want to give them? Do we expect a beginner to like learn? Anyways, I feel like my monologue of how I'm feeling right now is becoming incoherent. But the point being is like there's a trade-off between like complexity and beginner simplicity, and like what's the best version of this.
Yeah. So I have some similar doubts. I think I blame a different aspect on this. I would say, well, the thing with rank is that I guess I'll go into the move from axis to rank. I mean, so yeah, rank definitely works better than axis did as APL started. However, axis is a whole lot easier to understand. And I would say that's because it's more explicit in a sense. So the way I think of rank is sort of that it's, for array programming, it's a lot like assembly language, because it leaves everything implicit. It forces you to work out what is the number, the rank I want, and then you encode that in this very compact way. You say there's a single number that says what I want to operate on, but the axes of your argument arrays are something that you have to keep entirely in your head. So it's not like say assembly would deal with types. Each assembly instruction tells you what types you want to work on, but you don't have any high-level picture of what type is this value, what type is that value. You just say add as floats these two registers, add as ints these two registers. So I think the leading axis model in that way is very low level. So it's a really elegant representation of a low-level computation. But I am really also interested in looking at how would you express this at a high level. And the tool that I think does a really good job of that is it's not a general tool, and so making it a general tool is still a challenge. But Einstein summation notation, which you'll see in a NumPy package like einsum, which does give you, it gives names to all the axes. So I think the naming axes is a much higher level view, and I'd like to see a programming language that really takes advantage of that, which, I mean, the best we have now for that is really the old school Fortran paradigm, where you have each index loops over, this axis or that axis, and you index everything with brackets. But I think there's room for a much higher level view that takes array programming semantics but encodes them in a really different way to get. And your code would be longer, definitely, but it would also be more explicit and more naturally intuitive, and it would say what it's working with rather than just what it does to it.
Have you seen the or heard of the programming language Dex?
Yeah. So that is
Does that do something close to that?
a little bit. I mean, it does have named axes, but I think it doesn't really. Like you still manually line up all your correspondence between axes. So one of the ideas I've been thinking about is what you really would like is to say your function takes these two, like if you have matrix multiplication, you want to take a matrix with axes A and B and a matrix with axes B and C, and then like you should be able to add these matrices together, and it should know. I mean, maybe you have to say that I want to pair the equal axes, but it should know that axes B go together and A and C go on their own. So that's an idea that I've been looking at that I don't think Dex has anything like that.
Adam, do you have thoughts on BQN versus APL, like versus because like
I'm kind of double-minded about this because, yeah, it seems more pure like J already, and then BQN maybe takes it to extreme, but then it comes down to practical needs. It actually needs to get something done. Then I often find that okay, so APLs might be less powerful or like have more built-ins that are technically speaking redundant because you can easily do the same thing. But it's really convenient. I find that APL is much better at being at making the common actions easy. So the fact that let's say I want all the sums of the columns and the rows of a matrix. So it's like to check some like magic squares and things like that. The fact that I can write things like in APL plus slash bar comma plus slash as a fork. So that plus slash bar, that's the column sums, plus slash, that's the row sums, and I just concatenate together. Now I've got all the sums. That's really convenient. It even looks good, in my opinion.
Yeah, and so that's where BQN cells helps. It doesn't get you back to APL, but it gets you closer because you write plus fold, join with plus. Well, you want insert, not fold. Plus insert, join, plus insert cells. And so you've only got that one extra character in there. It's not quite as good as APL, but it's pretty close. Whereas in J, if you got the rank 1, it's not quite as nice.
Oh, but it goes much further, right? Let's say that we're dealing with like rotations of a matrix, flipping a matrix. And then it gets kind of ugly when you need to special decorators everywhere for all the different combinations of it. So Iverson actually I described this circle with a vertical bar or a horizontal bar, and there's also the backslash, which is transpose. And Iverson originally designed a ton of these symbols, like every combination of vertical bars and horizontal bars and things, so you can flip and mirror and rotate whatever, everything into whatever possibility exists. And APL part that down to just the 3 of them. But you can pair them up 2 and 2 to get what you want. And there, even more so, it gets kind of ugly to have extra decorators. I totally understand the reason why you would want that. If I was to make things from scratch, I might also do that. But there's still something about it just being so convenient and so intuitive that a circle with a vertical bar, it does things horizontally, and a circle with a horizontal bar, it does things vertically. That sounds opposite, but I mean, the bar is indicating the line of that you rotate over the mirror surface.
Yeah, and there's really nothing I can say about that. Yeah, it is nicer.
Yeah, it's yeah, there's something. I feel like a lot of the times what I want is like BQN plus dialog APL. Like there's like a Venn diagram, and like what was it yesterday? I tweeted the formula for number of permutations, which is like n factorial divided by n minus k factorial. And I realized that those 2 factorials, that's the psi combinator, and then n shows up twice, so you can use a dyadic fork, aka a phi 1 combinator, and then poof, in like 5 characters. And then I was like, all right, I'll go do this in BQN. and then BQN changed the factorial function to be an assert, and then I went to the page, and then there was no glyph for factorial, and then
you got to implement it yourself.
And then I was just like, oh well, this is an expression I like better in APL. But then half the time, because there's before and after, which are like, I think just because of before and after, like BQN edges out above any other array language, because they're just so convenient and like necessary in my opinion. If you're a combinator fan, but anyways, my point being here, because I'm just rambling, is that a part of me is like this trade-off of, you mentioned Iverson had originally designed all the different symbols, is like I'm just like, let's just have all the symbols. I want everything to be a symbol, but then obviously that's at some point there's a diminishing returns of what you're requiring. Obviously 3,000 symbols is too much, or is it? I don't know. The Chinese, you have to learn like 8,000 symbols to speak Chinese, so maybe it's not.
I think there's kind of an analogy here between modern automobiles and older automobiles. That what we've developed in automobiles is very efficient, very powerful, very controlled items that we really can't work on anymore. Because if you lift the hood, it's all hidden to you. And I think when you first meet one of these languages, what you're seeing is that kind of a thing. You see this thing that does this amazing thing for you whenever you want, does them really fast and really simple. I do this. But then you decide, I don't exactly want to do that. I want to do something slightly different. And what that requires is you have to go in under the hood and figure out what's going on in there, and then figure out how you're going to do it. And each of these languages gives you the tools to do that. But that level is never going to be what I would refer to as simple, because you actually have to know how things are working under the hood, as opposed to hopping behind the wheel and hitting the accelerator. And I think that's probably what you're hitting. And it doesn't make the languages harder to learn on an initial basis. But what I found, and what I really actually enjoy about J, why I still stay with J, is because that learning curve just keeps on going and going and going. There's always something more to figure out, at least for me. I think probably Marshall and Adam are beyond that. They're running off and designing their Ferraris and stuff. But I'm still learning that stuff that's under the hood, and it's just an ongoing adventure to find that stuff. You have to be able to want to do that to really enjoy those aspects of the language. I don't think it will ever be easy, but the languages are still very easy to use on the surface if they're doing what you want them to do.
I think there has to be some kind of level. Yeah, sure. You could have a super simple language that can do anything, technically speaking, except the humans can't keep up because it's too much work. Like some Turing tar pit language. Yeah, you can do anything. Of course you can. But you can't actually practically do anything. And then on the other end of the spectrum, where you provide enormous amounts of built-in things, and then the human can't keep up anyway, because you can't keep that vocabulary in the head. So you have to find the balance there somewhere. And there's not an exact science, and it's probably depends on the individual, so on. So I don't think there's much we can do other than making up some arbitrary constraints. Like K has a famous constraint. It's the ASCII symbols you can type on like a normal keyboard, the printable ASCII. It has to stay there, and numerics and letters, those are out because they use those for numbers and identifiers. And so all the special ASCII glyphs, that's the entire language basically. And I think both BQN and APL are limited also by the keyboard in a sense, but like you can only have two extra symbols on every key on a normal keyboard, and that's it. So both of them are getting to that limit, and that's
BQN hasn't really run up against it, and I'm not planning on going any further. So I would not say BQN is limited.
If I look at the BQN key map, pretty much every key has two symbols on it. Extra BQN symbols.
No, but there are a pretty good number of keys left if I wanted to add things. I just don't want to add things.
Yeah, the same thing for APL. There are a few more holes there. And I think that's a pretty good number. It's also interesting too, because think about the human interface things. Why do computer keyboards have the number of keys they have? Like standard keyboard, 100 and something keys. That seems to be like what humans can deal with. If you give them a lot of keys, then they don't know where to find them anymore. If you give them too few keys, then they're frustrated. That requires a lot of fiddling with shifting keys and so on to get to what they, or sequences to get what they need. So it's some balance like that.
All right, I totally lost track of time because I've just been one, enjoying this conversation and learning a ton, but also two, just like I'm lost in thought because I kind of just like Matrix downloaded a bunch of stuff into my brain. So now that I understand it, that's what I'll be thinking about for the next week while I'm going on runs. So
I know rank 2.
But Connor, did you notice that we've been speaking all about needing access and the rank operator and so on? We haven't even really gone into transpose and how important it is for all of this. So I vote that Marsha has to come back to continue this with the second part, which is transpose.
Yes, part 2 to come. I didn't even know that there was I haven't gotten to the point where I understand that transpose is important. But so the two things that I'll say now is that I think my big sort of eureka / epiphany is that it's these different ways. So these different ways to spell doing things on a row-wise basis, aka rank 1. So previously I had sort of read out, and I said mistakenly that it didn't work, but it definitely does work. So there's plus fold cells. That works on a matrix. There's plus insert rank 1, and that's the same way you would say the J solution is plus insert rank 1. And then in APL, it's plus slash, or so I'll say plus reduce is one way to spell it. There's also plus reduce first rank 1. And then I also tried plus reduce rank 1, which I didn't expect to work, but does when you use rank on, because reduce first is the leading axis theory version that is rankable, for lack of a better way to describe it. But can you also, is the reduce one also rankable, or is that just it works for rank 1 and doesn't work for other ranks? Or
it technically works, right? You can, but it has an inherent, so the normal, you're talking about reduced normal slash, right? That just looks at the rows. I mean,
yeah, which is, it's completely redundant to say rank 1 after it because it's already, that's the...
Yes, but you could do, I mean, not that it makes much sense, but you could do a rank 0 on it, and it will sum every number on its own, which would be no difference because a number itself added up is itself. But yes, it's still, rank operator is completely general, applies to any function, including plus slash. It's just not very useful because like you'd never want to do that.
If you used 0 as your rank operator with that reduce, and could you create each number being a list by doing the catenate in front of it?
Well, you
like, could you create lists that way of atoms, single atoms to lists, or does it work that way?
Reduce on one element never does anything.
Yeah.
It just returns
Right.
it.
Okay.
That's,
Which is actually kind of an inconsistency sometimes.
Well, in J, list
especially
on one element returns a one item list, right?
no.
If I catenate,
I
No,
don't think so.
I don't. Everybody's frantically typing into the J interpreter.
Well, Marshall types and figures that out. So the point here...
No, it gives you an atom.
Yeah.
okay.
So it doesn't. So reducing over a single element never does. Over a scalar never does anything. And
Okay.
if you do rank 0, then the function will only ever see scalars, and then not do anything. So not useful.
Yeah.
But does it apply? Yeah, technically it applies. It'll probably make performance be really bad. Doing nothing with terrible performance.
Although I do have to say that BQN just makes any reduction on a rank 0 array an error. Usually it says, if there's no axes, you can't do anything on that axis.
Interesting. So we've got reduces, reduce firsts, inserts and folds, and really the reduce from dialog APL is the odd one out kind of, because the reduce first / insert are the ones that sort of, we talked about the differences, or Marshall explained the differences. Anyway, so that's sort of my eureka. If you were a beginner and following along and you managed to have that eureka as well, then
you're no longer a beginner.
Yeah. So the last question.
I usually say that rank operator and dyadic transpose, those are the keys to the array kingdom.
Wow.
Right? Which if you master those, then the rest is just vocabulary, because those two together give you access to manipulate, in literal sense of the word manipulate, like literally twist your arrays around, exposing their insides in whichever way you want, and now you can apply things. What you apply is a matter of vocabulary, but those two things are what are essentials to be able to apply things.
And just to finish up what I was thinking about with the catenate, it was not reduce catenate item or rank 0. If you just catenate rank 0, that's what we'll do. It'll create lists of each individual one.
Oh yeah. That's Ravel though.
That's Ravel, yeah.
Yeah. So dyadic transpose rank sounds like the Eye of Agamotto from Doctor Strange. You got that. You can turn back time. I'm not sure if we have time for this last question, but it's less about the theory of this stuff and more, I think, was it Joel Kaplan on our last episode, or it might have been Stephen Apter, I can't remember which one of the two, but made a comment with respect to Arthur Whitney. I think it was Joel Kaplan who said that Arthur will throw away ideas when he'll come up with something, and then he's not afraid to let go of it, and made that remark specifically with respect to rank, and that sort of, as you mentioned, in 82 he was the one that came up with it, but then rank doesn't exist in K. Is there? Does anyone have any insight into Arthur? Does he think that rank was a bad idea and like came up with it, and then the rest of the array community ran off with it, and then he later on was just like, yeah, that was a bad idea. Or
No, not at all. I've seen the emails from him where he's even considering adding rank, or it would really be a depth operator to K as well. So it does have a little, just kind of like BQN has these shortcut monadic operators, which are just their big brother equivalents with a right operand of -1. So you have cells, which is really a specific instance of the rank. It's just rank -1. Then K has each, like APL and BQN has as well, and J has it as a keyword, or keyword, what's it called, the standard library word. So K has each, and then it has each left and each right. And each left and each right are very much specific instances of using the rank operator. And that is pairing up the entire one argument with each element on the right, or each element on the left. And then that means that you can then increase the rank on one side by adding multiple of these. You could say each right kind of thing. But they consider it fairly rare to need that kind of thing. But I've seen cases where they wanted that, and it became ugly to do it in K. And then Arthur reacted with, well, maybe it's time to introduce the general rank operator again. So I think he keeps it in the back of his mind, like it might be a possibility if necessary.
But there's no denying. I mean, this is just a question of trade-offs. And K is definitely an easier language to learn and use than APL. In some cases where you have high-rank arrays, K is going to be a lot more awkward to use. But it's also more straightforward to figure out what you need to do properly. So, I mean, K is a smaller, simpler language in terms of the primitives it has. And so there's, you definitely can't say that Whitney just made a mistake in removing rank. It's just that he chose to go in a different direction.
And I might be wrong about this, but I always get the sense when people talk about Arthur designing languages, he's designing for a purpose. And when he designed K, it's like you're trying to design a AA fuel dragster, right? You're not going to put coffee cups in it. It doesn't need them. Take them out. And then maybe down the road, there's something you go, you know what, but I could use power steering on this thing. So maybe I'll put that back in. Maybe that's worthwhile. But it's because his purpose is not to do a general purpose, I think, with K. It was to be able to go in and deal very quickly, very efficiently with huge amounts of data, specifically, I think, time-based. And that's what it's meant to do. So if it didn't need something to do that, out it goes.
Coming soon to a theater near you is a amalgamation of K, BQN, J, APL, all the languages, all the glyphs. My comment earlier on the fact that Chinese has you need what, 3,000, 4,000 to read a newspaper or something, and they all type in using pinyin, or like I even used to when I spoke Chinese and lived in China. You type the symbols in using a little pinyin. Maybe we should have a 3,000 character array language. I'm starting to that idea is starting to grow on me.
But and I don't know Chinese, but there's a basis of the ideographs, right? They're not just random.
Correct. Yeah, they're the radicals are what they're called. They have a radical for hand, a radical for wood and stuff, and you can find those in things that are wooden or things that require your hands and stuff. And like people is actually, I'm going to get that wrong because I'm thinking of the name of their Facebook, which is Ren, which is just person, I think. But anyways, yes, they have like patterns that you can sort of, you can guess what, oh, this has radical A and B, and so I'll take a stab at it that this is this, and you'll probably wrong, but you might be close.
And I'm guessing because of your interest in combinators, your foundation of those characters would be combinators.
Maybe. Definitely they'd tie in somehow. Although combinators, I mean, they're the hardest things to find symbols for, in my opinion, because it's very abstract what you're doing with them. But anyways, at this point, we're at like the hour and a half mark. I'm not sure. Our episodes just keep getting longer and longer. But any last things we want to say? This is awesome. Thank you for coming on, Marshall, and thank you for thank you to all of you for educating me. Hopefully, the listener or some of the listeners managed to pick up one or two things, and we didn't completely scare them away from the array paradigm. Adam,
I'll just say to the listeners, don't give up. It might seem really complex, but once these concepts click, you'll know it.
I mean, if they've made it to the end of this hour and a half episode, hopefully, we probably should have said that at the beginning. Maybe that's what you can do. Insert that clip at the beginning, Bob.
What I was going to say is whoever's still listening who's a beginner here, congratulations. You're amazing. I'm not sure this was a beginner's episode, but it might give you a sense of where to look and what to think about when you're using this. You can still use the languages on a sort of a more surface level, but if you really want to dive in, this is what you're going to start to learn. And as Adam says, when it clicks, boy, it's amazing. You really can do some amazing things with it.
And there's hope because, I've made it, a year and a half? 2019, we're in 2.5 years without fully understanding the rank operator. Clearly, for whatever amount of understanding that I've developed, I've done it all without really understanding the rank operator. So this definitely isn't something you need to learn on day zero. It's like Adam said, you unlock the full power of the matrix that APL and array languages have to offer when you can figure out the rank operator.
Well, dialogue made it about 30 years before they added this operator, so.
Oh, yeah, that's a good point.
There's that.
Yeah. All right. I guess if that's the last thing to say, we will finish this episode by saying happy array programming.
Happy array programming.